Good, very good. So now I'm recording this lecture video. So later when I finish producing that, I will share that with you guys in our Blackboard course. Okay. So in section 2.2, we talk about evaluating limits using the algebraic method. So we do have three different methods. The first one is called direct substitution. Meaning you should direct substitute x values into the limit and then find the limit right away. The second method is called a cancellation technique. And the third method is called a rationalization technique. We'll just quickly review this, each one of these methods. Okay, so let's start with the direct substitution. So basically, you can come up with any that kind of like limit x equals to 2. So let's say x cubed 2x minus 3, right? Something like that. And you can just substitute in all the x value with the given number. Okay, so we're gonna get 2 cubed, right? For that, the limit notion. Limit x approaches 2, we get 2 cubed plus 2 times 2 minus 3. And as you can see, it's going to be a constant x approaches 2, then we get 8, adding 4 minus 3. Okay, and simplify, you get 12 minus 3, that's 9, right? Limit of a constant is the constant. So the answer turned out to be. So this is exactly the direct substitution method. So I'm going to turn to our homework platform, to the workbook, and we're going to look at the question 13, which requires cancellation technique. So I'm going to use a show me another. So I'm going to just put in the screen. This is question 13. I'm using show me another option. So that's why you're probably going to have a slightly different question, right? But they are very, very similar. All the procedure will be exactly the same. Okay, so basically, in this question, if you do direct substitution, right, you can always try the direct substitution. And you fail, right? As you can see, you plug in a -4 into this. So if you try that, limit when x approach -4, you get x squared plus 3x 4 over x squared minus 16. Now again, I'm going to use a different color. So you plug in the 4, right? So right here, you can see limit when x approaches -4. On the top, we have -4 squared. Adding 3 times -4. Bottom, you're going to see -4 squared minus 16. And on the top, you have 16 minus 12 minus 4. Okay. On the bottom will be 16 minus 16. And we end up with a 0 over 0. And this is what we call the indeterminate form, right? Determinant form. We don't know what that is. And we get stopped. So that means direct substitution does not work. Then we're using then you jump to the second method called cancellation technique. That means we're gonna factor the top and bottom. So first of all, we're gonna factor the top. Okay, so let's factor the top. So you factor the top, you get this, which is -4. Now, on the top would be x plus 4, x minus 1.
Oh, it's just show me another.
Is any question? Ashley?
Oh, sorry.
Yeah, okay. All right, so that's so we factor the top, right? The bottom is the difference of two squares, so it's x squared minus 4 squared, and it becomes x plus 4, x minus 4. Okay. And from there, we're just gonna cancel the common factor, right? This one. Cancel that, and we end up with once you cancel the common factor, this process is called redefine the function. Redefine the function. So eliminate this kind of a zero scenario, right, in the denominator. So we do not have a zero anymore, right, in the denominator. So now let's do the direct substitution. We still go back to the direct substitution, right? Once you cancel the common factor, x approaches -4, it's x minus 1 over x minus 4. Now from here, we plug in the numbers, right? Plug in the -4. So on the top is -4 minus 1. On the bottom is -4 minus 4. Now, it's not an indeterminate form anymore. So we get a -5 over -8. And when you simplify, you end up with 5/8. And it's also 0.625, right? If you want to turn into a decimal numbers, we don't have to. Okay, so if you go back here, we end up with 5/8. And if you put in the answers here, 5/8, and we end up. So we get this answer 5/8. So if you submit it, check the answer, it's good, right? And do you guys have any question about this? Okay, so now no questions, very good. And let's take a look at the question 15. So we went over another example on the second method, right? Cancellation technique. Yeah. Now let's look at rationalization technique. Let's look at question 15 right here. Go back to the, so look at question 15. And again, we're using show me another option. Okay. And print screen. And we're gonna go over this, new. Question 15 from your homework assignments, section 2.3. And again, in the new textbook, it's the section number is slightly different, right? In the new textbook, in the like math edition, section 2.3 is the same thing as section 2.2 in our 6th edition textbook. Now, one more time, let's look at this problem here. Sure. Okay. So first of all, we still do the direct substitution. If you do direct substitution here, so plug in the 4, right, into the function itself. So get limit x approaches 4. On the top, we get radical 4 minus 3. That's 1. On the bottom, it's going to be 4 minus 4. But to simplify, you're going to limit 4. It's radical 1, square root of 1, that's 1. 1 minus 1 on the top, 4 minus 4 on the bottom. Again, 0 over 0. And we call 0 over 0 indeterminate. meaning nobody knows what that is, right? Even with all the tools we have so far in the mathematics, still no scientist or no mathematician can determine what is 0 over 0. So that's why it fails, right? So direct substitution fails. Then we gotta think about how to use the algebraic method to transform this rational expression. So one more time, this. Now we're using this conjugate concept, right? We learned from the algebra course. Meaning we're gonna multiply both top and bottom by what we call the conjugate of this rational expression. This case will be radical x minus 3 adding 1. You're going to multiply that to both top and bottom. Then once you do that, we're using this property called a minus b times a plus b, that we get the a squared minus b squared. And basically we get rid of the square root. Okay, so if you look at that limit, x approaches 4 here, and if you it becomes a squared is a minus b, a plus b, a squared minus b squared. You do radical x minus 3 squared minus 1 squared on the top. On the bottom, you keep as is. You carry over everything. X minus 3 adding 1. Now let's simplify the top. Become a squared, so square root, square offset each other. So this square root and square offset each other. So end up with x minus 3. 1 square is 1, right? Minus 1. That's on the top. On the bottom, minus 4. And then times radical x minus 3.
Professor,
Yes.
Maybe I think so that we should multiply the conjugate of the denominator.
Denominator, and it's a numerator, isn't it? So what do you mean is, let me just maybe quickly go over this one more time. For the denominator, it's okay. You see, the conjugate of the denominator there's no conjugate of denominator here. Okay, so that's why we're gonna multiply by the conjugate of the numerator. Can you share? I just accidentally exit that. Okay. Yeah, 1 second. Share. Just accidentally exit that. Okay. Let me go back to that new screen. Previous one. Yeah. Okay, so I accidentally close out that link, but it's not a problem. Okay, so I'm gonna share that one more time. Okay, yeah. So one more time, Shao, what do you mean by conjugate of the denominator? You mean you're gonna multiply the denominator by x plus 4? Is that what you mean?
Yeah,
Okay.
I think so. So that we can multiply x plus 4 with the numerator and denominator. Then our
But think about it. If you do that, then you get x squared minus 16, right?
yeah.
You plug in a 4, then what happens? You get 4 squared minus 16.
Oh yeah,
That's 0 again, right?
I got
So
it.
that's why. So that means whatever has radicals, right? We're gonna rationalize whatever has radicals, right? So for example, like in this case, we're gonna rationalize the top because once we rationalize the top, then we come up with the same common factor, x minus 4 on both top and bottom. just like what I showed you guys earlier. So right here, the conjugate. So it's going to be radical 3 minus 1 over x minus 4. Now the conjugate here is this radical thing. So we're just going to multiply by the conjugate plus 1 over radical x minus 3. Still, if you cancel this this common factor radical x minus 3 adding 1, we still go back to the original expression. However, once you rationalize the numerators, and then we get a, this is a minus b, this is a plus b. Now it becomes a squared minus b squared. So we end up with the radical minus 3 squared minus 1 squared. Okay, and on the top, on the bottom, it'll be x minus 4 times, carry over the whole thing, right? We do not change anything, just carry over that. Now let's simplify the top. Okay, color. If you simplify the top, this square and the square root will offset each other. So end up with x minus 3, 1 squared, that's 1 minus 1. Now, as you can see, it becomes x minus 4 on the top. On the bottom, you also have x minus 4. Now, the nicest thing is we can cancel that common factor here, right? This is the common factor because this is x minus 4. X minus 3 minus 1, that's x minus 4. Now, this is not a problem anymore because when we're substituting x to the 4, then it's not a problem anymore. So when you cancel that common factor, you get 1 on the top. On the bottom is radical x minus 3 adding 1. So now we can do the direct substitution. So it's 1 over radical x minus 3 adding 1. Now if you do direct substitution, no more 0 in the denominator. And that is what we want. That's the whole purpose of doing this third method called rationalization method. Technique, right? So you get rid of that 0 in the denominator. So when you plug in the 4, you get radical 4 minus 3 minus 1. No, adding 1. Okay. So it'd be 1 over 1 plus 1, that's 2. So the answer is half. All right. Any question about this? Now, if we go back, I'm just going to put in the answer. Half. Hey, see if that works. This works. So basically, that's just a quick review what we did from last week. Now let's if you guys do not have any question, we're gonna get started on next section about continuity. All right. And share the screen here. Okay. We're gonna get down to the section 2.3. On section 2.3 is mainly about continuity. Continuity is one of the main topics. Also, one side. And before we can define the continuity, we take a look at how we can define discontinuity. Anybody have a suggestion how we can talk? We can say the discontinuity. Okay, so I'm gonna give you some examples, right? Interruptions, right? On the graph, there's open circle, we call that a hole, a gap, or there's a jump, something like that. Right? All of those will give us a discontinuity. So first of all, I'm going to show you some graphs, and then we can look at how the discontinuity happens from a graphical perspective. So the first one is called look at it. Okay, so you're gonna let's say we draw something like this, and then there's a open circle here. And this is a typical discontinuity, right? If you look at it. And then basically we get a hole here, right? This is a hole. I mean, the graph of the function f of x is not defined there, right? So meaning this, let's say the coordinate c is the constant, right? Meaning f of c is not defined. And this is the first type of the discontinuity, right? When there's an open circle. Also say this is an open circle. Typically, we call this open circle. Graphically speaking, right? You get an open circle. And this is the first type of the discontinuity. Second type is, quickly show you. Okay. Let's say we have something like this. It's a piecewise function, look like this. Starting point here, and down below here, this is the open circle. Okay, and let's say this is C, right? And right here, f of c is defined, right? F of c is defined right here. It is defined here. However, there's a jump. This is what they call the jump discontinuity. Okay, there's a jump from one piece of the graph to the next piece. This is a typical jump discontinuity. And the thing is that if you look at it from the limit perspective, if you left-hand side limit here, x approaches c from the left, right? For f of x, is not the same as limit when x approaches c from the right. So basically, for all the jump discontinuity, this happens, right? Meaning limit does not exist. Okay, so the second type of discontinuity is limit when x approaches c for function f of x does not exist. And usually, one way to look at it is you're going to see something like a jump discontinuity. And so this is the second type, right? And also we have third type. Draw the graph quickly, and we can analyze it. Say third type. Right here, very similar to the previous one. We get this graph in here, and then there's open circle right here. And this graph look like this, and then right here, there's a solid point right below this open circle here, and this is what they call C, right? F of C is defined again. and then limit exists, right? First of all, for third graph, FC is defined. Right, that's one thing. Secondly, limit when x approaches c for this function f of x exists. Right? Limit is this. Take it right here. Right? However, limit when x approaches c for f of x is not the same as f of c. Does that make sense? Because f of c is here. This is f of c. Limit is this. This is the limit. They are not the same. So this is third type of discontinuity, and this one is what we call the removable discontinuity. Meaning to remove this, redefine this function by filling this open circle here, filling this hole using, once you, for example, like the earlier one, right? If you cancel this, if you factor the top, basically we redefine the function. Now it becomes a new function, right? Which is this x plus 1. So original function is x equals to, let's say, x squared minus 1 over x minus 1. Then once we redefine the function, then it becomes x plus 1. Only when x cannot be 1, right? That's why that's open circle right here. Okay, so this is the third type of the discontinuity called the removal discontinuity. Also, if you go back to the first example here, this is also called a removable discontinuity. These two scenarios, we can redefine a function and make it a removable discontinuity. Right? But they are both continuities. So any question about this? Okay, so now that's define the continuity, right? So once we understand all different scenarios for discontinuity, then we can define a continuity. So let's say you want to define continuity for f of x at x equal to c, right? So it must satisfy three conditions. Satisfy three different conditions. Condition number one. We just cover all three different scenarios. First one is f of c is defined. Meaning we eliminate open circle there at f of c. Secondly, limit when x approaches c for f of x exists, right? That means we eliminate jump discontinuity, which is in this earlier scenario. We eliminate this scenario here. Second scenario limit does not exist. So now limit exists. So we fill in the gap. So no more gap here. There's no more jump. And third scenario is this one, right? We're gonna satisfy the third condition, which is the limit when x approaches c for f of x is gonna be the same as f of c. In that case, we eliminate this scenario, third scenario, called the removal discontinuity. So the starting point will fit in the open circle here, right? The starting point will fit in the open circle. So in that case, we get a continuous, it's continuous at x equal to c. So the third scenario is limit when x equal to c for f of x. It's the same thing. So if these three conditions are satisfied, we're going to say that f of x out of b is going to be continuous as at x equals c. And that's how we define the continuity. Now, we're going to take a look at some more example of discontinuity. Okay, so now, first one is we already see that it's called a removal discontinuity, and some of them are non-removal discontinuity. So there are two types of discontinuity: removable versus non-removable discontinuity. For the removal discontinuity, we already see that first scenario. You see the graph earlier, something like this, a circle, and again, if you redefine the function, get removal discontinuity. Secondly, something like this, very similar graph. Right, we can fit in the open circle right there. This is still the removal discontinuity. Algebraically speaking, we just cancel the common factor. For the rational function. Cancel the common factor. That's how we get this removal discontinuity. And for non-removal discontinuity, that's the first type is called jump discontinuity. Right, we see an example earlier. Color. Something like this, right? Say you get this graph here, this is starting point, the other graph, this is open circle, and this is exactly the, at this C, right? This is exactly the jump discontinuity. We also have another one called the infinite discontinuity. So far, any question about this? Second type, what we call the infinite discontinuity. Now it has different type of graph, right? I'm just gonna show you some of the graph. You probably see this already in the pre-calculus or calculus class, pre-calculus class, or algebra class, something like this. Color, something. You can see this graph. This is a graph of the, let's say, f of x equal to 1 over x, right? And then at the x equals 0 right here. Now, if you look at the limit when x approaches 0 from the left, you're going to see that limit for x approaches 0 from the left for this function f of x is going to be negative infinity, right? This is where the infinite discontinuity comes from, right? Because as the x approaches 0 from the left, the y value keep decreasing without boundaries, right? Just keep decreasing. Limit when x approaches 0 from the right-hand side for function f of x. As you can see, this is increasing without a boundary, right? Just keep increasing without boundary. So it's infinity. That's where the name comes from, infinite discontinuity. And we also call this x equals 0 the vertical asymptote, right? Vertical asymptote. When you learn the when you take the pre-calculus, this is what they call vertical asymptotes. This is one type of them, right? Another type could be, let me just give you another graph. Still is what we call the infinite discontinuity here. So you look like this. Something like that. And this could be the graph for f of x equal to 1 over x squared. Okay, that's typical rational function, right? And as you can see, limit, this is 0 right here. When x approaches 0 from the left, for function f of x, you're going to get infinity, right? And secondly, limit when x approaches 0 from the right for f of x, it is also infinity. So that's what we call the infinite discontinuity. And as you can see, these two graph does not connect, right? At the x equals 0, it does not connect. That's where the continuity kicks in. That's one thing, right? So there's a gap between these two pieces of the graph. Right? So there's a gap here. The gap, there's a break. You can also say this is a break. There's a break on the graph. And this break happened to be the vertical asymptote, right? So this is the second type of the discontinuity right here. So let's go back to this, our homework system. We're going to look at some of the questions here on the identify what type of the discontinuity is this, right? So I'm gonna show me another. Okay, what do you think? Anybody have a suggestion? What type of discontinuity is it? Is it removable, jump, or infinite?
Infinite.
Infinite, right? Very good. Yes, great. Because if you draw the graph of this function right here, let's quickly just screen. Very similar to the one we have, just with a slight difference, right? The slight difference is that there's a transformation happening here, right? You just move this graph 10 units to the right. So the parent function for this particular function is the parent function. will be f of x equal to 1 over x. Now you subtract 10, meaning you move the function from this 10 units to the right, right? So the original function look like this. Now this graph here, the different color, it will look like this. So let's say this is 10, right? Now the graph function becomes this. So there's a break, right? So it's a, as you can see, limit when x approaches 10 on the left, f of x is going to be minus infinity, right? This is decreasing without boundaries. Just keep decreasing. Limit when x approaches 10 from the right, f of x, it will approach infinity here, right? On the bottom is negative infinity. And this one approaches infinity. This is negative infinity. So that's why this is what we call the infinite. Okay. Any question about this? And pick x equal to 10. That's where the discontinuity occurs, and this is called infinite discontinuity. All right, and that's the correct answer right there. And let's look at this one, right? Really quickly. I'm going to show me another example. So let's see where the function is continuous for this particular rational function. We call this rational function. Any suggestion? How do we get that?
Maybe we can find out the domain. Then yeah, in the domain it will be continuous.
Yeah, exactly. Right. So, very good, Sean. That's a very good suggestion. So here, so let's locate. Yeah, exactly. Find the domain. So the domain will be all real numbers except whatever number give us 0 in the denominator, right? So here the
5
domain,
and negative 5.
Exactly. So if you draw the number line here, this is original domain for all the function. And then as you can see, if this one equal to 0, then x equal to 5. If this one equal to 0, and x equal to -5. That means when x equal to either 5 or -5, then this function is undefined. Undefined means there's a discontinuity. So discontinuity occurs at x equal to -5 and x equal to 5. That's where the discontinuity occurs, right? And once you dig out those two discontinuities, meaning it's continuous everywhere except those two places. So as you can see on this graph, it's just going to put in -5 and 5. And this is an open circle here on the graph, right? Meaning it's not an open circle. It's just it's going to be what we call the vertical asymptotes, right? X equal to -5 or x equal to 5 is the vertical asymptotes. Now actually domain will be this. So the first place, second place, the first interval, second interval, third interval. So the function is continuous from -infinity to -5, union -5 to 5, right? Union 5 to infinity. And at what type of discontinuity occurs at x equal to plus minus 5?
Infinite.
Yes, very good, infinite. Because they are both vertical asymptotes, right? Vertical asymptote is what we call the infinite. Vertical asymptote is equivalent to infinite. So that's why it's an infinite discontinuity. All right, so that's basically how you analyze this. So this basically is how it's right. That's it. Yes. Go back. I'm gonna quickly put in the answer in our home system. We're gonna do minus infinity and f, right? We get infinity right away, minus 5. Close parentheses. We're gonna need a union symbol, or you can get a union symbol on the side, right? This is the union symbol on the sidebar. Right here, it will be -5 to 5. And then one more time, union symbol from 5 to infinity. Okay, so get that. So we get the 3 different intervals, right? They are continuous. Check the answers. It's good. All right. Let's just quick example on this. Now, basically, the 3 popular functions, right? For 3 popular functions, first one is called a polynomial functions. For all the polynomial functions, they are all continuous. I'm just going to give you a general expression, general equation for the polynomial functions. It's n power adding an minus 1 times x n minus 1 adding an minus 2 times x n minus 2, and we get the c. And we can keep going, right? We can just keep going. N minus 3 times x n minus 3, and I keep adding that, and until we get to the last couple ones. Let's say a2 x to the second, right? And adding a1 times x to the first, adding a0. And this is a typical polynomial functions, right? And the example could be, first example we learned is a linear function, let's say x plus 5, right? That's a first degree polynomial function, right? This is first degree. And we know it's a straight line, right? So look at it, it's a straight line, it's continuous everywhere. Secondly, second type of x equal to x squared, something like adding 2x, 3. And this is what we call the second degree. Polynomial function. And again, it's continuous everywhere, right? You're going to see a parabola, right? Something like this. Parabola concave up. This is a straight line, increasing straight line. And the third one, third degree. X cubed, let's say plus 4x, squared, and 2x, adding 1, something like that. This is what we call third degree polynomial function. And the graph will look like this. Increasing all the way, right? From left to right. And again, it's continuous everywhere, right? So for all the polynomial functions, it's continuous everywhere. On the entire domain, right? Continuous on all real numbers. meaning from negative infinity, infinity, they all continuous, right? And second type is what we call the rational functions. I'll just quickly adjust the screen a little bit. So the second type is we call the rational function. Also, what typical rational function would be r of x, right? Numerator n of x, denominator. Okay, let me use this. Numerator function of x over denominator, right? D of x. And here d of x cannot be 0. So that means for all the rational functions, continuous on its domain, right? So it's continuous everywhere on the domain. Continuous in entire domain. The domain will be all real numbers except whatever x value give a 0 in the denominator. Also, third type is radical functions. Radical functions. So the typical radical function is x equal to nth root of x. Again, it's as soon as this radical function is defined, and it is continuous in the entire domain. Continuous. In the domain. So for example, actually mentioned this earlier during the review section. So let's say function f of x equal to square root of, I'm going to keep it very simple, right? Square root of x minus 2. So basically the domain here, domain will be the domain here. Any suggestion?
X cannot be 2. Negative. Oh, sorry. X must be greater or equal to 2.
Okay, exactly, right? So it will be x minus 2 must be greater or equal to 0, right? Because it's square root, if it is a cubic root or fifth root, then it's all real numbers. Because of square root or the even root, you're gonna make sure whatever number under the square root or the even root must be greater or equal to 0, and 2 from both sides of the equation. So this is how we find the domain. Okay, then x must be greater or equal to 2. That means turning into an interval notation, the domain here will be 2, including 2, right? 2 infinity. Okay. So this is the domain, and then the function is continuous everywhere in the domain, right? If you look at the radical x, the graph looks like this. 1, 2. This is what a graph looks like, right? And it's a smooth curve, right? No break, no jump, no gap, and no open circles, right? It's very, very smooth within the entire domain from. And that's why we call this continuous in the entire domain. So again, we talk a lot about this different type of functions, also the continuities of the function. Let's look at some of the examples from section 2.4 homework. Down to the homework. Yeah, let's look at question 7. This is a very good question. Now, this is one of the tricky one, right? This, and let's see how we handle this problem right here. Now we get a different type of the limit, right? But so we have 3 different limit: left-hand side limit, right-hand side limit, and the overall limit. And this is what we call a one-sided limit, right? Again, if you look at this, what we call right-side limit. And the second one is called, it's the all under falling in the category of limit. Okay. They either have a left-hand side, right-hand side, right? Just 2 type of them. So that this one is left-hand side, left side limit. And this is what we call a general limit. By combining both the left-hand side and right-hand side. And we're going to take a look at the first one, right side limit. So let's see how that unfolds. All right, so now, how do we analyze the right side limit? So typically, you draw a number line, right? That's usually very helpful. And since we x approaches -17 from the right-hand side, let's say this is -17, right? And then right-hand side indicates we are moving towards -17 from the right direction, this direction. This is the right side. Okay, that's how we look at this, interpret this right side limit. And if you look at when x approaches -17 from the right-hand side, let's say you want to use a very, very close number here. For example, something very close to -17, but it's from the right-hand side. You use something like probably -16.9, right? Something like that. And when we talk about a table method for last class, we actually look at this type of number in order to estimate a limit. Okay. Now let's analyze it, right? So if this number, you adding this x value by 17, okay, on top, is it going to be positive or negative? Top. If this number is added to 17.
Positive.
Positive, right? So that means this is positive. If it is positive, then we don't need this absolute value sign, right? So we can get rid of it. Very important analysis here, determining the sign of this expression x plus 17, because it's positive. So we don't need this absolute value sign. Absolute value sign just guarantees this outcome is going to be positive, but since we know it's going to be positive for sure, we don't need it. We can get rid of it. By getting rid of it, right? So we basically get the same factor here on both top and bottom. So if you cancel this, you end up with 1 over 1. So it becomes 1. Okay. And basically this is what it looks like, right? When x approaches -17 from the right-hand side, the limit is 1. So the answer here will be 1. Now we look at the left side limit right here. So we're going to tackle the left side limit. Again, of course, the -17 from the left-hand side. So typically, if you want to use any number, right, any number you like to use, let's say you want to make it a little bit more obvious, you can use minus 18, right? That's definitely on the left-hand side of minus 17. If you put this into this question right here, so this first, second one, analyze the right side limit, no, left side limit. We already did the right side limit. Left. And again, if you have minus 18 throwing here, right? Because it's smaller than 17, minus 17. So that means top will be negative. We plug in that. But what if we want to get rid of this absolute value sign? What do we have to do? Let's say we don't want this absolute value sign. Anything, is there any algebraic transformation we could do to making sure this is going to be positive when we get rid of the absolute value sign? How do we do that? Any suggestion? All right. So the simplest method is just put negative sign in front of it, right? Because it's minus, so you put another minus in front of it, it becomes positive. And that's what we want. Right? We use them negating this. So basically, minus minus is plus. Because we know x plus 7, it has to be minus, right? It has to be negative. You put another minus in the front, it will turn into positive. And once we do that, then again, we see the common factors of both top and bottom. You can cancel that. That becomes minus 1 over 1 is minus 1. Now, from here, you know that the right side limit is not the same as the left-hand side limit. That limit does not exist, right? You know, limit here does not exist. So that's how basically how you analyze these type of scenarios. If you look at this function, quickly show you how to draw this graph right here. So you can view this as a function of 2 absolute value of x 17 over 17. Now, actually, we can turn this into a piecewise function. There are two types. There are 2 pieces here, right? First piece is x is less than 17. Second piece is x is greater than 7, minus 17, right? Yeah. If x is less than minus 17, less than meaning approaching this from the left-hand side. Right? That means that up here must be negative. So in order to get rid of it, we put a negative sign in front of it, minus x over x plus 7. Cancel that. Cancel the. So this is the first piece. And second piece, left. On the right, x greater than minus 17, right side. And because the top, because this is a positive, then we can leave it as this. And the bottom is that. So this is 1. So f of x equal to absolute value x plus 17 over x plus 17. It's the same thing as a piecewise function of -1 when x less than minus 17, x greater than minus 17 is going to be 1. So if you draw the graph of this, right here. Say this is minus 17. And this is 1, 1. Top is positive. On the bottom is negative. So less than minus 17 is minus 1. So your graph will look like this. Color. And then greater than minus 17, graph will look like this. Then if you analyze the limits, right? And from left hand side, limit approaches -1. On the right hand side, limit approaches 1. That's how we get that from the other screen earlier. That's how we figure out a limit. See, that's what type of discontinuity is this? Any suggestion? Okay. This is what we call the jump discontinuity, right? It's jumping from one piece to another. The typical jump. All the piece, most of the piecewise function will have this type of jump discontinuity. We'll see another example in a second. So any question about this? All right, so let's go back to the, so let's see. Side is 1, right? Left hand side is -1. And then the general limit does not exist because there's a jump discontinuity. So limit does not exist. Okay, it's all good. Now let's get to question 8. This is a very, very good question. Let me see if I can get a different graph. Is it different? Let's see. Slide 3. Yeah, it is slightly different. Somebody you show me another. Okay. Now, first of all, I want you guys to learn how to sketch the graph of this function here. I give you some time. You guys just try to sketch the graph for this piecewise function, right? Give you a little time to practice this. And then I will go over the solution in a second. So there are 3 pieces, right? First piece is this x minus 5. Second piece is x squared plus 1. Third piece is 3 minus x. So this is what we call the piecewise function. Okay. This is called a piecewise. In this piecewise function, we have 3 different pieces. The first piece is f of x equal to x minus 5. And the domain for that particular piece is less equal to -1. Secondly, second piece for x equal to x squared plus 1. And the domain for this piece is greater than -1, less equal to 1. Second piece. Third piece will be f of x equal to 3 minus x. And then that domain will be x greater than 1. Now I want you to sketch the graph, right? Based on this 3 different pieces, sketch the graph. Okay, try that. Give you a couple minutes. Try this one. while you're doing this, right, I'm gonna mark attendance for everybody so get credit for today's class. Don't worry, I just mark you on a syllabus. So Jim actually here, another Rajay, Erica, Ethan, Ter, Jamil, Junyon, Laura, Leo, Lenin, Sha, Xinyi, Eugene. Okay, I got you all. So do you finish yet? Okay. Okay, so let's go over the solution really quickly. But this is piecewise function, so we start with the first piece. Based on the understanding of the function, right? It's a linear function, meaning for any linear function, you only need 2 points, right? 2 points determines a line. Okay, so basically take the first piece. I'm gonna pick a couple points. The important thing is endpoints, right? Endpoints must be always there. So the endpoints here is the graph ends at -1. So -1 must be there, right? Also, we're gonna pick anything within the domain. This interval right here. For the endpoints, that's very, very important, right? We're gonna pick the endpoints, and then you know where to stop, right? Where the line stops. And so basically, so for the first one, you do f of -2. So you go back to the original function, replace x with the -2 minus y, which is -7. So the order point, order pair is -2, -7. And for control -1, that'll be -1 minus 5, which is -6. So that's the second order pair. Okay, and so from there we can graph this piece, right? The first piece, the line. I guess I will put them here. -6 base. Let me see. We try to do it in a different screen. Just copy and this and screen. So get a screen right here. Hi. One more time, we're still working on the first piece, right? For the pairs, did earlier, -2, -1. So you can pick any other number you like, right? But the -1 must be there because it's what we call the right point. And it's a solid point. This is the point which is defined as graph. And this is -7, right? So you get that first piece. If you're gonna sketch the first piece, we can do that, right? Let's just sketch the first piece. You see it. And the x value is -2. -1, -2. 1 -2x. And the y value, -7, right? Yeah. -1, -2, -3, -4, -5, -6. Now, first order pair, it's -2, -7. Second order pair is 1, -6. And both solid points, -1, -6. That's the right hand point, solid point. -2, -7. That's also a solid point. And then you connect them. Notice that the line stops here. Stop at right hand point right here. So then we take care of the first piece. Now, let's look at the second piece. Second piece will be f of x squared. In this piece, we get two endpoints, right? -1 and 1. And this is a parabola concaving upward. Typically, for parabola, you can have 5 points. But since we know the shape, we can simplify into 3 points. So 3 points will be good now. So remember, endpoints must be there, right? So -1 must be there, 0 must be there, and 1 must be there, right? -1 and 1, those are endpoints. And now from here, we're just going to get y values, right? We get y value from the function itself. So f of -1, that's going to be -1 squared, -1, 1 plus 1 is 2. 2 here. With 0, it's 0 squared plus 1. And with 1, that's 1 squared plus 1. It's 2. So basically, we have 3 points here, 3 order pairs, and the graph look like parabola. Let's get to the second. So -1 right here, and 0 is here, and then 1. Okay, -1, that's 2. So 2. And this is open circle, right? This one, 1, 2 is open circle because there's no equal sign here. And no equal sign, just greater than -1. So this is open circle. Oh, there's a hole there, right? Open circle. So right here, it's an open circle. Second point, 0, 1. This is a solid point. 1, 2, that's a solid point right there. Now you connect them, right? Connect them with a curve. We know it is parabola concave up. So you just connect it with a smooth curve. Right, so that's a second piece. Yep. So we take out the second piece, the third piece. Look at the third piece. Third piece here is f of x equal to 3 minus x, right? And then there's a left endpoint. We actually include a left endpoint. Left endpoint is 1. And again, it's an open circle there, right? With that, I'm just gonna pick 2. Just keep it as simple as possible. start with 1, it's going to be 3 minus 1, that's 2. And this is what we call the open circle. So 1, 2. 1 comma 2, it's open circle. Right? It's not defined from the third piece. It's defined on the second piece. Because 1, 2 here is a solid point on the second piece. Right? So it's open circle on the third piece. So this is the tricky part, right? The only tricky part about piecewise is a domain and also the endpoint. Once you nail down those, that will be very, very straightforward to sketch a graph. And number 2 will be 3 minus 2. That's going to be 1. 1. And that's also solid point. So here it's 1, 2 is open circle, right? However, although it's open circle, but it has been filled in by the second piece. Right? Second piece, a solid point, they occur at the same place. So this is filled in by the second piece. And 2, right? 2, 1. Yes, right here. Now you connect it, right? Get a third piece. And this is how you construct the piecewise function. All right. And now let's analyze it really quickly when at a -1. See what happened here. At a -1, that's a discontinuity, right? We also call this jump discontinuity here. So first one, limit when x approaches -1 from the left for function f of x. What would that be? So follow this graph here, approaches -1 from the right. Then the y value approaches -6. So it's negative. Secondly, limit when x approaches -1 from the right-hand side. And we're going to use a second piece, right? Here, follow the direction of the graph. Then the y value approaches 2. That's equal to 2. As you can see, left-hand side limit not equal to right-hand side limit. So the conclusion is the overall limit here for f of x does not exist, dne. Any questions so far?
I have a question.
Definitely, yeah.
Why is the one for x squared plus 1 why is it open circle?
X squared plus 1, right? Okay, actually, so basically, you see, you always focus on the domain. So for the second piece, the domain is, and this is the domain right here, right? It's x greater than 1 less equal to 1. So as you can see on the left end, there's no equal sign. X is greater than -1. There's no equal sign here, meaning it's not the function is not defined at the x equal -1 for the second piece. That's why it's open circle. Right? This sign determines it's open circle. And on the right end, right, because it's less equal to, there's equal sign here, and this sign determines solid point because of equal sign.
Thank you.
Yeah, okay, great.
I have a question, Professor.
Sure, yeah, sure. Yeah.
So there is basically one solid point and one hole at point 1, right? When x is equal to 1, there.
Yep, that's right. And 1, 2 is a solid point. You see, that's why it's a, you see, I bubbled that with the red earlier, solid red point, and that's a right end point. Left end point, it's open circle. That's why I put an open circle up there.
So if we have to graph, then how can we mark this one? Just a solid point and a open circle at the same time. How can we mark this? If we have to graph somewhere.
Oh, you mean at the x equal to 1, right?
Yeah, at x is equal to 1.
Yeah, that's why I've used a different color, just show you, you know, it's a solid point on the on the red graph, but it's open circle on the blue graph. So it's a starting point on the second piece, but it's open circle on the third piece.
Okay, I got it.
However,
Thank you.
that open circle on the third piece has been filled by the second piece with a solid point, because they happens at the same location, but the coordinates are exactly the same. That's why you see we're fitting with that.
Thank you, Professor.
No problem. So this is a very, very, very good question. See, this determines the outcome, because the fourth part is asking you guys limit when x approaches 1 from the left for f of x. As you can see, if you analyze this, now approaches 1 from the left. Okay, this is from the left, then the y value approaches 2. Okay, and then the fifth one, I think they ask in limit when x approaches 1 from the right hand side. As you can see, let me use a different color so you see what happens there. You just follow the direction here, move closer and closer to that. You see that the y value also approaches 2. So that's also 2. And now for this one, the limit exists. And then is this continuous right here at a 1, 2? That's a quick question at a point 1, 2. Is it continuous?
Yeah, it's
It
continuous.
is, right? Yeah, very good. So this is where the interesting thing is. The limit exists. Limit converges to the same number, and then it's continuous. So because it's part of the one condition for the continuity, right? So f of 1 is defined. That's one thing. Limit when x approaches 1 exists, right? Limit when x approaches 1 is the same thing as f of 1. So it satisfies all three conditions, 1, 2, 3. That's why it is continuous there, right? F of 1 is defined. And then limit when x approaches 1 for f of x exists. We verify with this, right? Exist. And limit when x approaches 1 for f of x is the same thing as f of 1, which is even better. So now all three conditions satisfied. Now that's why it's continuous. This is continuous point here. Very good. And what is the last part? They ask you, what is f of -1 here? F of -1?
Discontinuous?
Yeah, it's discontinuous, but what will be the y value at x equal -1? If you look at it, you look at the solid point here, right?
-6.
-6, exactly. So that's why domain it helps, right? Determining the y value for that discontinuity that happens because it could only be defined on one piece, not both pieces. That's why f of -1 in this case will be -6. Now let's go back to the original question here. I can answer all of this. For -1, we did it, right? Does not exist. Now from the right hand side, right? Right hand side of -1. So now let's forget the graph for a second, right? What if we're just gonna use the algebra to solve this? How can we do it? Any suggestion? Like without looking at the graph, right? We know we can use the graph, not a problem. What if you just want to look at the function itself, determine which piece does this approaching -1 from the right? Which piece are we going to use to get the y values here?
X² + 1.
Yeah. S² + 1, right? But exactly, that's the piece we're using here. Very good. And then basically all you have to do is locate a piece, locate a function we are going to use, which is the second piece here, and replacing x with the -1. You look at -1 square, right? -1 square, adding 1, and that will be 2, right? And then if you look at how we get it from -1 from the right is 2. When we look at it earlier, right? -1 from the right is 2, right here. Yeah, so that's why all these different methods, there's different way of looking at this. Graph, we can visualize that, but you can actually solve it without a graph. So that's why we end up with the 2 here. And then -1 from the left, which piece are we using here?
X minus 5.
Exactly, very good. Yes, that's exactly right. Actually, so that will be -1 minus 5, right? So 1 minus 5, we end up with -6. And we can always double check with the graph. If you have the graph, you can double check. Approaches -1 from the right, it turned out to be -6. So we are using the first piece right here. So we take out that one, that's good. Now we know the overall limit does not exist, right? So that part DAE. And then approaches 1, we did it earlier, right? Left-hand side is going to be 2. Right-hand side is going to be 2. They both converges. So we do left-hand side using the second piece, right-hand side using the third piece. They both happens to be the same number 2. So the limit exists. Limit when x approaches 1 for f of x is 2. Okay. And what is f of -1? Which piece are we using here? This one, right? X less than or equal to -1. So using the first piece. So it'll be -1 minus 5. And that turned out to be -6. That's why yeah, we did it earlier with the graph, and it's the same answer here. And this is without using the graph, right? You can locate a piece for that particular limit and then do the direct substitution to find it. Okay, so that's how we solve this type of problem. Now I'm gonna take a look at question 10 really quickly. Now, let's look at this question quickly. So before I end the class, so we want to locate the removable discontinuity and then non-removable discontinuity from the algebraic perspective. How do we do that? Any suggestion?
We just remove the what did it say? A common factor.
Right, exactly. Very good. So basically, so you look at this function here and then factor both top and bottom, just like, and if we factor the top, we're gonna get x minus 8, x plus 5. On the bottom, it will be x plus 5, x minus 5. Now, the removable discontinuity comes from the common factor. Meaning, whatever you cancel, right? That's the removable discontinuity. So this is the removable discontinuity here. At the x plus 5 equals 0. That means x equal -5. It's a removable discontinuity. Whatever remains, that's a non-removable discontinuity because we cannot redefine that point. We cannot redefine the function. So when we cancel the common factor, we are redefining the function. That renders the removable discontinuity, and then whatever we cannot cancel, right? That's a non-removable discontinuity that happens at x equal to 5. Does that make sense? Yeah, so we do have a couple of discontinuities, right? The discontinuity occurs at the -5 and 5. right? That's good, because when x equal to -5 and 5, we get two discontinuities, but one of them is the removal discontinuity. Removal discontinuity occurs at x equal to -5, and then non-removal discontinuity occurs at x equal to 5, right? That's what we analyzed earlier, non-removal discontinuity at x equal to 5, and that's going to be the answer. Okay. No, actually, it's discontinuity removable. Yeah, they're asking for removable, so it's -5. Non-removable is 5. Okay. So yeah, I guess I will end the class right here. And we go back to normal, right, next week. This is just one-time deal. I know it's a snowstorm, it's pretty bad outside, so for your safety, you know, they decided to hold a class via Zoom. But I will see you guys in class next week. You should finish all the homework assignments all the way up to 2.4, right? We just finished 2.4. We're gonna start the I will tell you what to review. I sent you email reminder later. We're gonna probably review the infinite limit and also the other limit from the other section. I will send you the email reminder later this week. So before we end the section, do you have any question? Okay. So again, if I finish producing this, I did record this lecture video for today's class. I will post it in our Blackboard course. Okay, and you can review these lecture videos. Go over the homework assignments, right? It will help you get better understanding of the topics. Okay, I see you guys next Tuesday then. Bye bye, guys.
Bye, Professor.
Bye, Professor.
Goodbye.
Thank you, Professor.
Happy New Year.
Bye bye. Happy New Year. Thanks. Okay. Happy New Year.
Thank you,
Bye-bye.
Professor.
No problem. Bye bye, guys. See you next Tuesday.